This section will present individual components of a hypothesis test. We should know and understand the following: how to identify a null hypothesis and an alternative hypothesis. The null hypothesis we're going to represent with this symbol H sub naught. Naught is an old-fashioned term that means zero. And then the alternative hypothesis, you will either see a H sub 1 or an H sub A. And 1 and the A are subscripts. We're going to look at how to calculate the value of a test statistic. We're going to look at what a test statistic is. We're going to choose a sampling distribution that's relevant, and a lot of this is going to feel very similar to what we did in Chapter 7. And then we're going to learn how to identify a p-value, learn what a p-value is, and the critical values, and then how to state the conclusion about a claim in simple and non-technical terms. Our first definitions: a hypothesis is simply a claim or a statement about a property of a population. Usually we're going to make a claim about a parameter for the population. And the hypothesis test is the procedure that we're going to use for testing that claim about a property of a population. One of the central things that we tend to follow is what's called the rare event rule for inferential statistics, which basically says if under a given assumption the probability of something happening is very, very, very small, then we're going to conclude that the assumption is probably not correct. Not that what we observed is impossible, but that our underlying assumptions were false. Now, I talk about the assumptions because whenever we're doing tests of hypothesis, we assume the null hypothesis is true. And if we get a very low probability of what we see happening with that assumption that the null hypothesis is true, then we have to conclude that our null hypothesis is not true, which means it's false. We test the null hypothesis directly in the sense that we assume it's true and reach a conclusion to either reject or fail to reject the null hypothesis. Some of the forms that a null hypothesis would take on would be something like the null hypothesis would be that a parameter p maybe is equal to 0.25. Remember, the parameter p is a proportion or a percent. Or we could say that test a claim about a mean and say that the mean is equal to some numeric value, say 150. Or we could test a claim that a standard deviation is equal to 1. These are sample null hypotheses. Whenever you're writing a null hypothesis, they all take on the same form. You have H sub naught for the null hypothesis, and then you're going to insert your parameter. And then in your null hypothesis, you always have equality, and it's going to be equal to some number. This is the form that a null hypothesis takes on. What is in red will always have to be the same for every null hypothesis. What I have written in blue here is what will change depending on the claim that you're testing. An alternative hypothesis never contains equality. The null is the only hypothesis that contains equality. It never contains equality. We're either going to use less than, greater than, or not equal to in our alternative hypothesis. This is also sometimes referred to as the research hypothesis because it is the only hypothesis that can be proven true. The null hypothesis is never proven true because we assume that it's true whenever we run tests. The symbolic form will take on an inequality, either a strict inequality or just simply not equal to. Let me show you what the alternative and null together would look like and what this kind of means to us as we go through our process of testing hypotheses. If our null hypothesis is that some proportion is equal to 0.25, then our alternative hypothesis would look like this. No, p is less than 0.25. That would be an acceptable alternative hypothesis. In this situation, we would call this a left-tailed test. And what it would look like is this. If we were to graph the situation, we would have our normal distribution. And since our alternative is claiming that this is less than 0.25, we would end up with our rejection region over here to the left. And if I wanted that rejection region to be 0.05, we would call alpha, remember that I said that that's our significance level of 0.05. That means if we assume the null hypothesis is true and we run some mysterious test right now because you don't know what it looks like, and we end up with a value that's down here in this red rejection region, also called the critical region, then we would say no, that null is not true because there's a very small chance of getting what we got, assuming that's true, so our assumption is wrong and therefore we've proven the alternative is correct. That's why the alternative is the research hypothesis. It's the only hypothesis that can be proven true. Now, the critical value here would be equal to negative 1.645. And how we ended up with that negative 1.645, remember, is we went to our calculators and we would do inverse norm of 0.05, and that's where that negative 1.645 came from. And that was our critical value, and it's the same critical value we got whenever we were doing 90% confidence intervals in Chapter 7. Now, this is a negative number because this is a standard normal distribution. You know it's a standard normal distribution because the variable I'm using here is z, and z is the variable we use with a standard normal distribution, which means the mean is 0 and the standard deviation is 1. Another example of a set of hypotheses we could do would be one like the null hypothesis, where the mean is equal to, let's say, 150, and the alternative would be no, the mean is greater than 150. I'm just showing you samples of what an acceptable null and alternative would look like. In this situation, where the inequality is going to the right, we would have what's called a right-tailed test. And the picture that would represent this would look like so. We would have our normal distribution, or it could even be a t-distribution if sigma is unknown. Either way, the middle value is 0. And here, if I used alpha equals 0.05 for our significance level, this would be our critical region, this red shaded area, and the critical value that separates the critical region from the not so critical region would be 1.645. And how you could find that on your calculator is by doing inverse norm. The question was, is this significance level always going to be 0.05? Sometimes it's going to be 0.01 if the seriousness of what you're studying is more significant. The significance level typically in social sciences will be 0.05, but sometimes in medical research we'll use 0.01. It's related to the confidence level. The confidence level, if we were doing a confidence interval, would be 1 minus alpha. Now this has to change to a 0.95 because remember the inverse norm gives you, it uses the area to the left of the z-score that it's finding. Now you could just use the fact that we have symmetry, and if this is negative 1.645 over here, this would be positive 1.645. Common sense would tell you that. Or you could put in the correct area here. So that's a left-tailed test, a right-tailed test, and then we also have a two-tailed test. In a two-tailed test, I could say that the mean is equal to 75, and say I wanted to say the class average on the test is 75. And I would come up with an alternative and says, no, it's not 75. I don't know if it's bigger or smaller. I just know it's not 75. It's different from 75. So in this situation, we have what's called a two-tailed test. And how this looks different is it looks more like what our confidence intervals did whenever we had our rejection region going on both tails. So here, if I'm saying not equal to some numerical value, I don't know if this is going to be smaller or larger than 75. I just know it's going to be different. So I can reject it if it's too small or if it's too big. And by it, I mean the test statistic that we don't know how to calculate yet. So in this scenario, alpha, if it's 0.05, this critical value is not going to be 1.645, it's going to be 1.96 and negative 1.96. And how do we come up with these numbers? This value right here is not going to be alpha. That area is going to be alpha over 2, which means that we're looking at inverse norm of 0.025, which is half of the alpha level, the significance level. What I want to point out here is whenever you have your null and your alternative hypothesis written, you will be able to identify whether or not you have a left-tailed test, a right-tailed test, or a two-tailed test simply by the alternative hypothesis. Notice the inequality here points in the direction of the tail of the test. Here we would reject the null hypothesis, If our test statistic fell down here where it was too small, well, that arrow, if we think of that inequality as an arrow, is pointing to the left. Here we would reject the null hypothesis if our test statistic was too big, and that, if you think of it as an arrow, is pointing to the right, so it's a right-tailed test. If you have not equal to, you will reject the null hypothesis if your test statistic is either too small or too large. So one of the things I want us to do right now is practice identifying, writing the null and the alternative hypothesis for given scenarios. In this question it says, in each of the following situations, is the alternative hypothesis one-sided or two-sided? And then what are the hypotheses? So we're going to practice writing null and alternative hypotheses. Part A here says, a college dining service wants to know if students prefer plastic or metal cutlery. They conduct a survey to find out. If students don't have a preference over metal or plastic, what % would prefer, say, metal? If they don't have a preference, what would you expect to see? If there's no difference in the preference, you would expect maybe half to say plastic and half to say metal. So our null hypothesis here, remember the null hypothesis always contains equality. So that would be our proportion is equal to 0.5. In the alternative, notice up here, whenever I wrote my null and my alternative, the parameters were always the same and the numbers were always the same for the null and the alternative. So here I know that this is going to be p for my parameter and 0.5 for the number. The question now is, what is the symbol that goes in between the p and the 0.5? An inequality, not equal to. We don't know if it's going to be for plastic or for metal, so we're just going to say not equal to 50-50. We want to know, do they have a preference? So if they have a preference, then the proportion that say one or the other won't be 50-50. So this would be what kind of a test? On Part B, it says, in recent years, 10% of college juniors have applied for study abroad. The dean's office conducts a survey to see if that's changed this year. What would our parameter be here? A proportion, a mean, or a standard deviation? Proportion. And we would have p equals what for our null hypothesis? 0.1. So our null hypothesis is p equals 0.10, and our alternative then would be p is not equal to, because we just want to know, is it different? Is it changed? Not more than or less than or something. We don't have any idea. We just want to know, is it different? All right, in Part C, it says a pharmaceutical company conducts a clinical trial to see if more patients who take a new drug experience headache relief than the 22% who claim relief after taking a placebo. Does everybody know what a placebo is? It's kind of like a sugar pill. It's where you think you're getting a treatment, but you're really not. When they received a placebo, 22% of the people in the study felt relief. If a treatment is really effective, what do we expect this number to do? Go up. We expect to see a greater proportion. There's key words in the problem that indicate that this should be bigger, should be more. This is a what kind of test? Right-tailed. And you can tell because the inequality is pointing to the right. Part D, it says at a small computer peripherals company, only 60% of the hard drives produced pass all their performance tests the first time. Management recently invested a lot of resources into the production system and now conducts a test to see if it's helped. What is our null hypothesis going to be here? 0.6. 60% of the hard drives passed their performance tests the first time. The alternative, we expect to see that percent go up that passed their peripherals test or performance test. And this would also be a right-tailed test. Learning how to spot what the claim is and how to write your null and alternative hypothesis is a skill that will get better with practice. That's why we have homework. Notes about forming your own claims or hypotheses. I had already mentioned before that the alternative hypothesis is also referred to as the research hypothesis. And I'm going to see if I can help you understand a little better why I say that the research hypothesis is the only one that we can prove to be true. And I'm going to do this by relating the null and the alternative to something that most of us are familiar with because we've watched television, and hopefully not because we've been a part of the criminal justice system. So when somebody's arrested and they go to court, we say that they are presumed innocent. This is the assumption that we start with. So that's our null hypothesis. If that assumption is not true, we have our alternative, and that is guilty. And this has to be proven. And it's proven by showing that this assumption, the chance of having that assumption be true and all of the evidence be against this person is so small, we have to reject that assumption. Now I ask you, do we ever prove anybody is innocent? I've never once heard somebody declared innocent by the judge. What do they say? Not guilty. Saying not guilty is not the same thing as saying innocent, is it? No. As a matter of fact, it's impossible to prove somebody's innocent. We can just show that there's not enough evidence to claim that they're guilty. So therefore, this is the only hypothesis that is able to be proved. This hypothesis is proven by being able to reject the null hypothesis, reject that they're innocent. The probability that the null hypothesis is true and that it's rejected is equal to our significance level, alpha. That's why we want this number to be very, very low. The probability that someone is innocent and we reject that they're innocent, that's like sending an innocent person to jail. We want that probability to be low. That's why we set our alpha level so low. And the more critical it is that we have this not happen, the lower the alpha level will be. So the more serious the thing that you're studying, the lower that alpha level will be, the more critical that mistake is. By the way, if we were to do this, this is called a type 1 error. If we send an innocent person to jail, that's a type 1 error. If we let a guilty person go free, that's a type 2 error. In our system of government, would rather see a guilty person go free, 10 guilty people go free, than one innocent person go to jail and their freedom be taken from them. That's the way our court system is designed. So does that kind of help you see that we never accept a null hypothesis? We just fail to reject it. We never accept a null hypothesis, just fail to reject it. F2R is my abbreviation for fail to reject. It's so much shorter than writing it all out. Steps 1, 2, and 3 for identifying the null and the alternative hypothesis. By the way, have you noticed I keep switching back and forth between using a subscript of 1 for the alternative and a subscript of A? You're going to see it written both ways, and I'm used to writing it both ways, so it's not a conscious thing on my part. It just happens. The first thing you want to do is identify the specific claim or hypothesis that's to be tested and put it in symbolic form. That's what I was doing up here when we were going through this example. I was writing down the parameter in symbolic form and what the claim was. Is it equal to, more than, whatever. Step 2 is give the symbolic form that must be true when the original claim is false. The null and the alternative are essentially opposites of each other. They can't both be true at the same time. Of the two symbolic expressions obtained so far, let the alternative hypothesis be the one that does not contain equality, so that the symbols greater than, less than, or not equal to are used. Let the null hypothesis be the symbolic expression that does contain equality. So here's the example problem we're going to use throughout this chapter. It's that XORT method for determining the sex of a baby. It says assume that 100 babies are born to 100 couples treated with the XORT method of gender selection that is claimed to make girls more likely. We observe 58 girls and 100 babies. Write the hypothesis to test the claim, and now here's the claim. With the XORT method, the proportion of girls is greater than the 50% that occurs without any treatment. There is the claim. Can you write that claim in symbolic form for me? P is our parameter, its proportion, greater than 0.5. So now let's write our null hypothesis for this claim. Our null hypothesis would be P is equal to. The null hypothesis always contains equality. The alternative then is that P is greater than 0.5. Now this author used to teach this to where the alternative, if this was greater than, then the null would be less than or equal to. Finally, he just gave it up and said equal to, because that's what other authors were doing, and essentially that's what we're testing. If it's not greater than, then it's going to be less than or equal to, and we'll just say equal to. Write the claim in symbolic form, and that claim, if it contains equality, will be your null. If it doesn't, then it will be the alternative. The null hypothesis always contains equality. It's the only hypothesis that contains equality. Alright, step 4 is to select the significance level of alpha. Remember what alpha is? It's called our significance level, but it's also the probability of rejecting the null hypothesis and that null hypothesis is true. The company would hate to see this happen. No, actually the parents would hate to see this happen. They would hate to have you reject the null hypothesis when it was true. Because if you reject the null hypothesis, you're saying that XOR method worked. And if it doesn't really work, why do you want to pay so much for some genetic selection? Significance level. The significance level, denoted by alpha, is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true, making the mistake of rejecting the null hypothesis when it's true. This is the same alpha that we used in 7.2. Common choices for alpha are 0.05, 0.01, and 0.10. If you're not told what significance level is, assume it's 0.05, just like we did in Chapter 7. Step 5, it tells you how to identify what the test statistic is and determine the sampling distribution. These are exactly the same sampling distributions we used when creating confidence intervals in Chapter 7. If we were creating a confidence interval on a proportion, we would use the normal distribution with these requirements. This is now our test statistic. The test statistic is just a z-score in this case. The P and the Q here are values from the null hypothesis. P and Q use the assumed values from the null hypothesis. In the mean, when we're testing a claim about a mean, if the standard deviation is not known and our original sample is normally distributed or our sample size is sufficiently large, we would use the t distribution, which remember depends on the degrees of freedom. The mu here is from the null hypothesis. It's what we would assume to be true whenever we're plugging this into the formula. Same thing here if the standard deviation is known. When we're testing a claim about a variance or a standard deviation, this number down here would be the one from the null hypothesis. Whatever parameter it is that you're testing, that's what we use there. So all of these values here are from the null hypothesis. Alright, our test statistic is a single numerical value that's used in making a decision about the null hypothesis. If you were to draw this graph like we did whenever I was talking about the tails on the test, and you plotted your test statistic, and it fell somewhere over here in this region, let's say that our test statistic fell right here, whatever it happened to be, we would reject the null hypothesis because that test statistic fell in the critical region. If your test statistic fell over here in the clear, then you would fail to reject the null hypothesis. And those are the only two conclusions you can make, by the way. You can either reject the null hypothesis, and that's what you do if your test statistic falls over here, or you would fail to reject the null hypothesis if your test statistic fell in that clear region. Step 6 is to find the value of the test statistic, then find either a p-value or a critical value. The p-value is the probability of getting the observed results, assuming the null hypothesis is true. Remember I said that whenever we're doing a test of hypothesis, we start with the assumption that the null hypothesis is true. Then we do some experiment and we collect data on either the mean or the proportion or the standard deviation, whatever it is you're interested in testing. We did an experiment. We took observations, recorded observations. We got the results from either that experiment or observation. If, based on that experiment and observation and the assumption that the null hypothesis is true, if these test statistics are extremely small or extremely large, meaning they fall in this critical region, then we're going to reject our assumption. Not the results that we gathered, but we reject our assumption. That's why I said if the p-value is small, then we reject the null hypothesis. Now, small will be determined by whatever your significance level is. If your significance level is 0.05, then small would be anything less than 0.05. A p-value less than 0.05 would be small. This picture I think does a better job of drawing than what I did, but the explanation is just as good. If you're doing a left-tailed test, your null hypothesis will contain equality, your alternative will be less than, and your critical region is over here in the red. Any test statistic that falls over here we would fail to reject. On a right-tailed test, equality in the null hypothesis, always equality. The inequality would be pointing to the right or greater than, and your rejection region or your critical region would be over here to the right. In a two-tailed test, we would have the equality for the null, not equal to for the alternative, and our critical region could be at either end here. Just kind of reviewing that concept. A p-value is the probability of getting a value of the test statistic that is at least as extreme as the one represented in the sample data. The critical region in the left tail means that the p-value would be the area to the left of the test statistic. So for example, if I had a test statistic that fell right here on a left-tailed test, this area right here would be the value of my p-value. How I would find that area would be I would use the normal CDF and go from negative infinity to my test statistic, and that would give me this area right here. I'll go you one better. We're going to be using the tests on the calculator, and it's going to tell you what the p-value is without you having to calculate it and use number crunching. But I want you to understand the concept behind what that number is. So if your critical region is to the right, let's say that our test statistic fell over here, then this region right here that I'm shading in would be the value of our p-value. That area to the right is smaller than this red region right here, so we would reject our null hypothesis. On a two-tailed test, if our test statistic ended up on the right, we would take the area to the right of the test statistic and then double it, because we have to have a matching area on the left on a two-tailed test. So that's why we would take twice the area of the tail beyond the test statistic. But like I said, we're going to be using our calculators here. It's not going to be that big of a deal. For example, the claim that the XORT method of gender selection increased the likelihood of having a baby girl results in the following null and alternative hypothesis. Here's your null hypothesis. Here's the alternative hypothesis. We already wrote those out. Here's how we come up with the test statistic. Our p-hat was the 0.58 because we had 58 out of 100 babies that were girls, minus our assumed value for the null divided by the square root of p times q over 100. That ends up giving us a 1.6. So this test statistic of z equals 1.6 has an area of 0.0548 to the right. That's the p-value right here. This value right here is the p-value, and this value right here is our test statistic. We can do this on our calculator. Instead of doing a 1 proportion z interval, we're going to do a 1 proportion z test. If the last letters are tests, that means you're performing a test of hypothesis as opposed to finding a confidence interval. And I'm going to go into greater detail on this in 8.3, so don't stress out over this. So we're going to do a 1 proportion z test, so that's test 5. This tells you the name of the test right here. This is the value of your null hypothesis. Our null hypothesis was that p is equal to 0.5, so we put 0.5 there. X is the number of successes. We had 58 girls born out of 100 babies, and we said this is a right-tailed test because our alternative was p is greater than 0.5. So we move our cursor down, and we actually are going to calculate this, and I want to show you what information your calculator will give you. It will give you the name of the test. This is your alternative hypothesis. There's your z-score that we got from using that formula for the test statistic. This number right here is the p-value. That means that the area to the right of your test statistic is 0.054, and that would cause us to fail to reject the null hypothesis. This is p-hat. We had 0.58 or 58 out of 100 bursts, and that's your sample size. The number crunching part is going to be easy. It's making the decision and stating the conclusion that you guys are going to have to focus on. Let's look at another p-value problem. It says, have harsher penalties and ad campaigns increased seatbelt use among drivers and passengers? Observations of commuter traffic failed to find evidence of a significant change compared with 3 years ago. Explain what the study's p-value of 0.17 means in this context. So we have a null hypothesis here and an alternative hypothesis that yielded in a p-value of 0.17. Now, our null hypothesis would be that the percentage of people who are using their seat belts is the same as it was 3 years ago. I don't have to know the number in order to do this problem. Our alternative would be, is it greater than, less than, or equal to 3 years ago? And what in the problem will help you determine that? Well, you've got to look at the claim. What is the claim? Increased seatbelt usage. So this is not a two-tailed test, it is a right-tailed test. I think life is easier when we draw pictures, so let's draw pictures to see what this represents. Because it's a proportion, I know that I'm going to be using a normal distribution, a standard normal distribution. There's 0 right there. Did they tell us what alpha level to use here, what significance level to use? They didn't tell us what significance level was used, so we're going to use alpha equals 0.05. If alpha equals 0.05, what is the critical value that separates this critical region from the rest of the distribution? It's 1.645. How did we get that number? Inverse norm. Now, we ended up with a p-value of 0.17, which means the area to the right of our test statistic, because it was a right-tailed test, that means the area to the right is 0.17. We weren't told what that test statistic was, were we? But we could find it on our calculator, couldn't we? That means that this area was over here. That area right there is 0.17. If that area is 0.17, what is this area over here going to be? 0.83. So to get that test statistic, I could do that the test statistic is equal to inverse norm 0.83. We get 0.95. So this is the z-score right here. So this is actually 0.95. 0.95 is clearly smaller than 1.645. That p-value is bigger than our alpha value, so we would fail to reject the null hypothesis. Our conclusion here is fail to reject the null hypothesis, but you never want to leave this written in that way, just reject or fail to reject. You want to write your conclusion in terms of the original problem. So our conclusion here would be something like this. Here would be the conclusion that you would use. Yes, you failed to reject the null hypothesis, but now you need to state your conclusion in terms of the original problem. The original problem said, have harsher penalties and ad campaigns increase seatbelt use among drivers and passengers. We would say there is insignificant statistical evidence to support the claim that harsher penalties and ad campaigns have increased seatbelt use among drivers and passengers. We failed to reject the null hypothesis. That doesn't mean that we've proven that it's the same percentage of people as it was 3 years ago. We just can't say that it is increased. I can't say that the percentage of people using seatbelts is the same as it was 3 years ago. I can't say that. That's too strong. What I have to say is there's insignificant evidence to support the claim that more people are using seatbelts. Here's a flowchart you can use to go through how to find your p-values, but I think I've explained it significantly. If not, shoot me an email. The critical region or the rejection region, and you've heard me refer to this region as both ways, is the set of all values for the test statistics that cause us to reject the null hypothesis. Basically, it's that red zone, and I will consistently use red for that region because red means danger. Reject. The critical values depend on the nature of the null hypothesis, the sampling distribution that applies, and the significance level alpha. So for example, for the XOR birth hypothesis test, the critical value and the critical region for alpha equals 0.05 are shown below. The critical value is the number that separates the critical region from the rest of the distribution. In this case, with alpha equals 0.05, we get 1.645 for our critical number. That means this critical region here is 5% of the area under the curve. When we did the test of hypothesis, using the information that was provided about the 58 girls out of 100 births, we ended up with a test statistic of 1.60. 1.6 is right here, which means that our test statistic fell in the clear. To me, this is in the clear. This is the region where we failed to reject the null hypothesis. So that would be our conclusion with that example for the XOR gender selection technique. So we conclude then that there's not really any difference between using the XOR method and nature. Would the p-value here for this data be larger or smaller than 0.05? All right, let me ask that another way. How do you determine the p-value concept-wise? Remember this. This is the output we got from the calculator. This number right here is the p-value. This number represents the probability of getting 58 out of 100 births, assuming that there's a 50-50 shot at getting a girl. That number's bigger than 0.05 because the p-value is the area to the extreme side of that test statistic. This area is bigger than the red area because it covers the entire red area. So when I ask you, based on p-values, would we reject or fail to reject this, you would say that number's bigger than 0.05, fail to reject. Looking at the test statistic, it fell in this fail to reject zone, in the blue zone on the graph. I would still fail to reject. We would reach the same conclusion whether or not we use the p-value method or the test statistic method by looking at the graph of the test statistic. When you use the test statistic method, you need to know this critical value. Now, don't confuse a p-value with a proportion. P is the population proportion. Up here in this problem, P was the percent of girls that we had in birth. Typically, we expect 50-50 because there's two sexes and we assume that they're equally likely. The p-value is a probability. It's that area to the extreme side of the test statistic, either left or right. So if your test statistic falls to the left of 0, it would be the area to the left of your test statistic. If your test statistic falls to the right of 0, it would be the area to the right of the test statistic. Guys, I cannot stress to you enough the importance of getting down the information in this section, because if you get this information down, the rest of the sections are just going to go like that. They're going to make so much sense, because all we're doing now from this point forward is we're looking at specific examples. This section is the big picture. That's what I'm hoping that you get out of this section. There's not much time left in this semester. We're about to start rocking through these sections rather quickly, but it all hinges on your understanding of this. This is going to be the Rosetta Stone for the rest of the course. Make a decision. Either reject or fail to reject the null hypothesis. Never, ever, ever accept the null hypothesis, because it's the value, remember, that we assume to be true. You can't accept or prove an assumption. There's two methods we can use to determine whether or not we reject or fail to reject. The p-value method, that uses a significance level of alpha. If the p-value is less than or equal to alpha, reject the null hypothesis. If it's greater than alpha, fail to reject. There has to be a cutoff number. Alpha is it. Even if it's equal to, we would still reject the null hypothesis. So if we do a test and our alpha level is 0.05 and our p-value is 0.05 exactly, we would reject. But if the p-value is 0.05001, we would fail to reject. There's got to be a cutoff somewhere. 0.05 is it. The critical value method. What we do is we plot our test statistic and we plot our critical value. If the test statistic falls within the critical region, reject. Otherwise, fail to reject. That's what I was doing up here with this example. If you need to review the video, back it up. I was going over the p-value method and the critical value method. And I've already gone over this example with the picture above. So using a p-value method, we would fail to reject the null hypothesis at alpha equals 0.05 because our p-value is equal to 0.0548, and that's greater than alpha. So we'd fail to reject. Using the critical value method, our test statistic, 1.6, is to the left of the critical value, which means that if you're doing a right-tailed test, which is what this was, our critical value is over here, 1.645, and our test statistic is right here, really close, but not exactly it, 1.6, and that's in this fail to reject region. We reach the same conclusion. We have to reach the same conclusion. The destination is the same regardless of the path you take to get there. The next thing you want to do is restate the decision using simple and non-technical terms, and this author is kind enough to provide a flowchart to help us do that. So starting out, we had a null hypothesis of p equals 0.5, an alternative hypothesis of p is greater than 0.5, and this happened to be our claim that more than 50% of babies are going to be girls using that XOR method. So does the original claim contain the condition of equality? In our problem, no, it didn't. Do we reject the null hypothesis? No, we failed to reject the null hypothesis. So we word our conclusion in, there is not sufficient sample evidence to support the claim that the XOR method is effective. Caution, never conclude a hypothesis simply with the statement reject the null hypothesis or fail to reject the null hypothesis. I've already gone over this. We never accept the null hypothesis. Never, ever, 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 ever. There's two types of error, type 1 and type 2 error. I went over this whenever we were talking about using a court trial with the null hypothesis that you're innocent, the alternative that you're guilty. You're either innocent or guilty. There is a truth about that, even though we, the public, may not know that. So this column right here, these two columns, reference the truth of the statement for the null hypothesis. It's either true or it's not. Using the court trial again, let's say that the null hypothesis is that you're innocent. The alternative would be that you're guilty. We make a type 1 error if the null hypothesis is true, yet our decision is that we reject the null hypothesis. Where this column and this column come together, we see we have a type 1 error, that's alpha. We rejected the null hypothesis when it was true. That means we put an innocent man in jail. If we reject the null hypothesis and the null hypothesis is false, we made a correct decision. Go over to the next column. If the null hypothesis is true, that means the person really is innocent. If we fail to reject the null hypothesis, we found the person not guilty, we made a correct decision. If the null hypothesis is false, and we fail to reject the null hypothesis, if the null hypothesis is false, that means the person really is guilty. We failed to declare them guilty. We let a guilty man go free. If we're looking at the sorting method for the XOR, alpha here, the type 1 error, would be the probability of what? We rejected the null hypothesis and said that the XOR method works. So we claimed then that the XOR method worked when it really didn't. We're going to have some unhappy parents. So here we would be claiming part B to this question asks us to identify a type 2 error. We use a Greek letter beta in order to represent the type 2 error. The type 2 error is the probability of failing to reject the null hypothesis when the null hypothesis is false. How can I phrase that in terms of the XOR method here? Who's upset here, the parents or the company? The company is upset because we claimed the method didn't work when it really did. So here the parents are upset with alpha, the company is upset with beta. We've got to find a balancing act. Controlling for type 1 and type 2 errors. For any fixed value of alpha, an increase in the sample size will cause a decrease in beta. Remember, alpha is the type 1 error, beta is the type 2 error. For any fixed sample size n, a decrease in alpha will cause an increase in beta. It's a balancing act between the alpha and the beta. Conversely, an increase in alpha will cause a decrease in beta. They're inversely proportional. If you raise one, the other one goes down. If you lower one, the other one goes up. To decrease both alpha and beta, you've got to increase the sample size. That's the only way to get both alpha and beta, the type 1 and the type 2 errors, to go down. The larger your sample size, the more reliable the results. This wraps up section 8.2. This is a critical section. Please do not slack on this section.